Ever wondered how the warmth from a fire can reach you all the way across a room? Or why a metal spoon you leave in a hot soup gets scorching hot almost instantly? Well, it all comes down to the science of heat transfer. So let's dive into this amazing journey of energy and motion. So, here's our game plan. We're going to break down the three fundamental ways that heat gets around. We'll explore conduction, then convection, and finally radiation. And then we'll see how understanding these forces lets us build some pretty brilliant stuff. All right, let's start with the big picture, what I'm calling the journey of heat. And trust me, this isn't some abstract physics thing. It is happening literally everywhere around you all the time. We all get what heat feels like, right? It's just thermal energy on the move. But how does that energy actually travel? How does it get from point A to point B? I mean, whether it's moving through a solid object like your coffee cup or across the vast, empty vacuum of space. The answer? Well, it lies in three very distinct processes. And here they are, the big three: conduction, convection, and radiation. Each one describes a totally unique way that heat moves around. Once you really get these three, you'll start seeing them in action absolutely everywhere. First up is the one you're probably most familiar with, even if you don't use the name: conduction. This is, put simply, heat by direct touch. So, the most important thing to get about conduction is that it's all about direct contact. It's one molecule all energized and vibrating, bumping into its neighbor and passing that energy along. The key here is that the molecules themselves aren't actually traveling, just the energy is. This is the perfect way to picture it. Imagine a long line of dominoes. The first one tips over, transfers its energy to the next one, which passes it to the next, and on and on. That's pretty much exactly how conduction works on a molecular level. It's a chain reaction of energy transfer. But here's the thing. Not all materials play the game the same way. This chart shows you exactly why that metal spoon gets hot so fast. Metals like copper have really high thermal conductivity. Their molecules are great at that domino rally. But things like wood, and especially air, are terrible conductors. We call them insulators. And that's why a big puffy jacket keeps you warm. It's trapping air, which is a great insulator, and stopping your body heat from conducting away. Okay, on to our second force, convection. Now, if conduction is all about passing energy between molecules that are more or less staying put, convection is about moving the hot molecules themselves. This is heat being carried along by a flow. The key phrase here is fluid motion. Convection only happens in things that can flow, so we're talking about liquids and gases. The heat literally gets picked up and carried from one spot to another by the moving substance itself. A great way to think about this is boiling water in a pot. The water at the very bottom gets heated by the burner, right? As it heats up, it expands, becomes less dense, and starts to rise, carrying all that thermal energy with it. Meanwhile, the cooler, denser water at the top sinks down to take its place, gets heated up, and the whole cycle just keeps repeating. That circulation is what we call a convection current. And convection itself comes in two main flavors. You've got free or natural convection. That's driven by those density changes we just talked about. Think of hot air rising from a radiator. Then you have forced convection. That's when we bring in a tool like a fan in an oven or the water pump in your car's engine to physically push the fluid around and speed up that heat transfer. All right, time for our third and final force. And this is the one that lets us feel the sun's warmth from 93 million miles away. It's radiation. This is heat that travels through invisible waves. Now, what's absolutely wild about radiation is that it doesn't need a medium. It doesn't need molecules to bump into or a fluid to flow through. It can travel right through the perfect vacuum of space, which is exactly how all of the sun's energy gets to us here on Earth. So, next time you're standing near a campfire, that heat you feel on your face, it's not just from hot air hitting you. That would be convection. A huge part of that warmth is infrared radiation, traveling directly from the flames to you as electromagnetic waves. And this is where things get really, really powerful. See, the amount of energy something radiates isn't a straight line. The Stefan Boltzmann law tells us that if you double the absolute temperature of an object, you don't just get double the radiated energy. No, you increase it by a factor of 16. It's an incredible leap, and it's why a red-hot piece of metal feels so intensely hot compared to something that's just a little bit cooler. So there you have it. Conduction, convection, and radiation. But understanding how they work isn't just for physicists. It's the key to all kinds of engineering.
So let's look at how we can actually master these forces and put them to work.
A thermos, or a vacuum flask, is just a masterpiece of thermal engineering. It's designed with one specific purpose: to defeat all three forms of heat transfer, to keep hot things hot and cold things cold. Let's break down how it does it.
First off, the vacuum. Remember, both conduction and convection need molecules to transfer energy. By sucking all the air out from between the inner and outer walls, you create a vacuum. No molecules means you've stopped those two forces dead in their tracks. Then you've got the reflective coating. The inner chamber is basically a mirror, and its job is to fight radiation by reflecting the thermal waves right back where they came from. And finally, you have the insulated stopper, made of a poor conductor to plug the last possible escape route for heat. It's just a brilliant triple-threat defense.
And the thermos is just one example. Controlling these three forces is at the very heart of so much of our technology. It's in the cooling fins on your computer's processor, using convection to whisk heat away. It's in the shiny heat shields on spacecraft that reflect the insane radiation of re-entry. It's even in the way we cook our food. Understanding this journey of heat gives us the power to really shape our world. The only question is, what will you do with that power?